Since we last left off with, see, we did the box on ramp problem, right? Ah, okay. I'll need some technical information in just a second. Once I get the basic drawing down. I assume we gave some angles.
50 and 40 degrees.
50 and 40? Yes. And coefficient of friction on right side or left side?
Friction in the left, 0 in the right.
Say that again?
Friction in the left, you have a mu s 0.5, a mu k 0.3. And in the right side, mu equals 0. That's the flux B, and the left is A.
Did it give masses?
Mass is B, MA 5 kilos, MB 8 kilos.
Does this capture the essence of what we were doing?
Yes.
The acceleration was also going that way.
Ah, that was the assumption that we made. All right. So first, because in order to know which way friction is going to act, we need to know which way the thing wants to move. So we're just going to assume acceleration in that direction. Did I give you an initial, I said it started at rest? Or did I say?
Don't think so.
All right, let's just go ahead and set that down. The initial speed is 0 meters per second. So of course, what is the first step?
Identify your forces. Or you can write down the, I forgot what it's called.
Oh, okay. So the checklist. So we're on this part right here, and more specifically, I heard someone else say it.
Force diagram.
Yeah. So we need to break it up into objects. Since we're assuming that this wedge here is not moving at all, it's in essence part of the ground. I'm going to draw that lower on the board. Then we have A over here, we have a rope, and then we have B. And as mentioned last time, and I feel like for years, but you missed it for the past several years. Try to draw these at the same orientation that they are in the original problem. I think it's easier when it comes to doing normal force to do it that way. All right, so doing the force diagram, let's put down our checklist for the forces. What do we got?
Friction. Against box in.
Except we don't know which way that's going to go yet. So right now we're going to assume when we're doing a problem like this, we make the assumption first that there is no friction just to see which way it's going to go. We'll add friction in when we do it the second time.
So there's tension in the.
All right. So I've got some tension here, some tension here. Those are supposed to be in opposite directions. Draw that a little bit more like that. Since it's in a single ideal rope, we assume that the tension is the same throughout. Magnitude of the tension. Since there's only one rope, and we've taken care of both ends, we are done with tension.
There is weight acting down on both the boxes.
All right. So W sub A and W sub A acting up. W sub A acting sub B, and W sub D. And I'm drawing them on the wedge because, again, the wedge is part of the planet. If the wedge were separate, I would not draw them there. I have only two objects. Again, this is part of the ground. So, gravitational force, done.
There's normal force,
Acting which way on what?
acting on the box away from the ramp.
Okay. Perpendicular also. Call that y sub b, y sub b, y sub a, y sub a. That's the only oh, wait, no, there's one other normal force pair.
Wonderful.
From,
The rope.
yeah. And again, I don't know exactly where, it's gonna be somewhere in that range right there. Not enough information to know the precise direction of that angle, but y sub t, y sub t. But it's somewhere in that general area. The exact direction is irrelevant to the problem. And we're including this just for completeness. It's really, when it comes time to doing our equations, I care about the two masses here, because it's an ideal rope and pulley, so I'm not worried about those. Normal force is done. Friction, we're going to wait. Just put not yet. What about other?
Don't think there is any.
And if Kyle thinks it, let's make it so. That potentially came across as sarcastic. That was not meant to. That was meant to treat you as a god. All right, so what is the direction of the acceleration of A? Since we're done with the F part, so it's now time for acceleration. Which way is A going to accelerate? All right, so this is going to accelerate in that direction. Which way is B going to accelerate? The magnitudes of the accelerations are the same because the rope doesn't stretch. It's not like A can move without B moving. They'll move the exact amount of, move the exact same distance in the same amount of time. So I'm going to use the same letter to represent them. Unlike with master set 6, problem 3, the one with the mass 1 on top of mass 2, you perhaps haven't seen it yet. Part B, they will have different accelerations, so you'd have an A sub 1 and an A sub 2. Coordinate system. Now, this is a situation right here where it'd probably be good to have a different coordinate system. For this one, I'm going to have one of them in the direction of my acceleration, and the other one perpendicular to that. Now, whether I make J pointing away, wow, I cannot do from an angle. Use my back. Better. Whether J points away from the ramp or towards the ramp is really irrelevant. The important part is that I is in the same direction as acceleration. And for B over here, I'm going to have this one going up. So call IB. J sub B. That I sub A and J sub A. Let's concentrate on the two items that we care about here. A, so I have weight of A acting down, normal force of A acting that way, and tension pulling that way. And there's our coordinate system. And then for B, I have tension acting this way, weight of B acting that way and Y sub B acting that way. All I've done is just rewrite what we have over there. So coordinate axes, done. D. What's D stand for? For the grammar purist, for what does D stand?
Decom.
Do we need to decompose anything?
Yes.
What do we need to decompose?
The weight.
All right. Now, we've gone through the geometry before, but if the angle that you're given is relative to the horizontal, oh, we've done that. I'm just gonna call this theta A and theta B. We'll plug in the real numbers at some point. But I can break weight up into down the ramp and into the ramp. This will be W sub A sine of theta A, and W sub B cosine of theta B. Same logic as we went through before. And here, down the ramp, W sub B sine of theta B, into the ramp, W sub B cosine theta B. And again, what I'm doing is I am going to replace this weight acting straight down and write it as these two right here. Kind of like a substitution. So A, we have Y sub A pointing that way. W, oops, got a wrong letter there. That should be A. W cosine, WA cosine theta A. WA sine theta A. And then for B, tension acting this way.
So you determine sine and cosine, like their direction, after you define your coordinate system?
Well, we have to define the coordinate system first to know what needs to be decomposed. Because if I set my coordinate system up like this, then WA is fine and I have to break these two up. And it's a real mess if you want to do it that way. So once I had to define this first, so now this one is not along one of the axes. And then the other thing is I needed to make sure what is theta. If theta is the angle off the horizontal, then it's going to be sine down and cosine in down the ramp. I don't know if I actually answered your question or not.
Sorta. You gave me like multiple ways to get to that.
Is part of the question about why is it sine and cosine?
No, I
Okay.
know why it's sine and cosine. I'm just saying, like, how do you determine exactly like where they go? Like, for example, right there you have sine theta on this side and then cosine on the other side for the box B. But I guess it's because you define your coordinate system
Oh.
that way. Yeah, I think you did answer it when you said the coordinate system.
Okay.
But you have to define it before you go into that problem.
Okay. I will trust that it's been answered, but if not, it'll pop up again and you'll ask again. I'll give the same answer and we'll just keep going in a cycle. No, hopefully we'll end the cycle next time. All right, any other questions? All right, decomposition is done. Now what?
Isn't the E stand for equations?
Yeah, which equations are we looking at?
F equals ma.
That's the big one right there. Equations of motion is what I generally call it. F equals MA is my template. how many equations of motion will we have? You look like you want to answer, Marcel. No.
4.
Yes, what for?
Um,
Or which for?
for 1 for each of the weight decompositions.
So what? I'm not quite sure. Need that, Austin?
So you're gonna have, one describing J hat motion in forces for box A, one describing I hat forces for box A, and then one I hat forces for box B, and one J hat for forces, on box B as well.
Yeah, that's what I was looking for. I don't know if that was the intent of, I think it was Max.
I was saying like W of A sine and then W of A cosine, 1 for each of those.
Oh, okay, okay. All right, so we've got our IA, JA, IB, JB. All right, someone want to go for it? Give me one equation. Or start us off on an equation and tag team to someone else.
WA sine theta A minus FT equals mass of A times acceleration.
Boom, one done. All right, next one.
I was just gonna say, like, when writing equations as acceleration, you have to have the arrow above it or not?
No, because officially, if I wrote this out far more formally, this equation is WA sine theta A I hat, I A hat, minus FT I A hat is equal to M A times A I A hat. Technically, that's the acceleration right there, but because all of them are in the same, along the same line, we just don't need to write that.
Okay.
In essence, we factor it out, and I don't know if you can really divide by a vector, but we sort of divide by it.
Okay. WA cosine theta A minus YA is equal to. Is it just mass times acceleration?
That,
Maybe.
there's two issues.
I'm not confident.
Okay. There's one fundamental issue with this, and then there's another one which is almost nitpicking, but I want to be clear on the other part.
Is it y of A minus W of A cosine?
All right, so that's one of them. The fact that we I guess I did it. I defined that to be the positive direction, so technically YA is positive.
Okay.
So if that's positive, that's negative. All right, that's the one that, if you correct the other mistake, that would have worked itself out. That actually, you would have come out with the same answer. But what's the other mistake?
Acceleration is 0.
Yes, and that's the whole point of setting up a coordinate system this way. Acceleration is down the ramp. There is no acceleration in that direction. So it's mass times 0, or just 0. All right. A new voice. Someone just wanted to take a chance.
Where's the coordinate system for B?
The coordinate systems that, let's see, I formally wrote it right there. All right, y sub b.
minus WB cosine theta b. Equal to 0.
Yep, all right. 3 down, 1 to go.
Would be f of t minus wb sine theta b equals mb sine theta.
Yep, there we go. We have our 4 equations now. At this point, if you were doing this on your own, say on a test, and that's not some strong hint, there's gonna be some problem on the test dealing with this general topic, but you're feeling pretty good about yourself. You're thinking there's nothing he can throw at me that I can't do. I want to keep that. Actually, I want to keep that. I'm gonna get rid of this. All right, time for substitution. For what do we have an equation? An independent equation that is like just a generic formula.
Weight equals mass times acceleration of gravity.
Thank you. So our equation becomes MAG sine theta A minus FT equals M sub AA.
What equation did we use?
That weight is equal to mg. And so anywhere there's a weight, we're gonna stick an mg. Now, at some point, you'll be comfortable enough, and instead of writing weight to begin with, you'll just write mg, or sometimes I might do it also. I mean, it's a WB being equal to mg, you can bypass this step and just write it sooner. From the second equation, we have y sub a equals m a g cosine theta a. And then the third equation, we have tension minus mbg sine theta b equals mba. And the last equation, yb equals mbg cosine theta b. Dramatic pause for questions and people to catch up in the writing.
Sure this is still going. Yep.
All right, we're solving for acceleration here. Now, this equation and this equation, the two J equations, are not going to have any impact this time around. When we throw friction into it, it will have impact, but for right now, it does not. So I'm going to take my two equations here and solve for acceleration. I'm just going to add them. You could solve for f of t in one equation and stick it into the other, or just solve them simultaneously by adding them together. And I got MAG sine theta A minus MBG sine theta B equals M sub A plus M sub B A. The FT's canceled out because I have one positive, one negative. The right-hand side, I'm solving for acceleration, so I can factor that right-hand side. So this is M sub A plus M sub B times acceleration. And so I have a formula for acceleration in MAG sine theta A minus MBG sine theta B divided by NA plus NB. Questions about this, how we got this far?
So why did you, okay, so I think I understand, but, why did you choose those two equations?
I want to find the acceleration. Well, ultimately, I'm trying to figure out which way this thing is going to go.
Right.
So, which in essence is going to be acceleration. That's the variable that describes motion specifically. And so, I know that part of it is, I've done this enough, but I know tension is an unknown, and so if I add them together, tension's going to go away. And also, they both have acceleration in it. So that's one of the main reasons. If I had added them together and I still had some other variable that I don't know, then I'd have to go back and go, oh, all right, what did I miss? I hope that's sufficient.
Yep.
Okay, awesome.
So how does that work when those are on two different coordinates?
Ultimately, the direction of every single one of these terms is the same as everything else in that equation. This is YB J sub B minus WB cosine theta J sub B equals 0 J sub B. And so, since they're all in the same direction, we're good. We could have written just one really long equation here, where some terms will have that, some terms will have that, some terms will have that, some terms will have that. But it goes back to, if I've got 5x plus 2y is equal to zx plus my, a solution, if this is always true, then z has to be equal to 5, m has to be equal to 2.
Sure, but I think my question goes, to be more specific, what I'm saying is that I sub a hat and I sub b hat are not necessarily equal to one another since you set your coordinate systems.
Right, oh,
like
agreed,
that,
agreed.
right? So how do we, are we just able to do it and that's just why we're able to do it, or?
Well, I was hoping that was justification. All right, so
Do you see what I'm saying though? Am I clear?
I believe so. I'm
Okay.
gonna get to the answer first, and then I'm gonna try to address it.
Okay.
So I'm gonna make a little note over here. There's a good possibility I'm just not gonna see this note, and then in about a half hour, I'm gonna go, oh, I forgot to answer it. So if I start, after we get an answer, if I start to move on, you can just say, hey.
Sure.
Hopefully that's enough to remind me. All right, any other questions? Obviously, need to get back to that one. All right, so at this point, it's plug and chug since we have everything here. I am assuming it takes place on Earth, even though I did not state that. So, Earth, some generic place on Earth. And somebody actually already done this. What'd you get?
Negative number, it's -0.989,
Negative 0.989.
yes. Well, around it's 0.988.
No, that's not what I'm indicating.
Oh, meters per second squared.
All right, there we go. What does this tell us? This answer has a physical meaning.
That means acceleration doesn't mean that.
Yeah. We picked the wrong direction. And that's because there's no friction involved, it's not like we have to change any forces. None of these forces here are dependent upon the direction it moves. But we have established that it is going to accelerate that way. And so now we know the direction that the friction is going to be on A. Dramatic pause for questions.
At the beginning, why did we assume it was going, why did we have to assume it was going that direction?
We have to figure out which way it's actually going to move. And this technique, although there are some shortcuts you can take, this technique, we needed to work through it in order to see if we get a positive or negative value here. So you just assume, you make an assumption which way you think it's going to go, work through the problem. If you get a negative, oh, it's the other way.
Okay.
So acceleration must be positive?
If acceleration is positive, well, if this thing starts at rest, and then I let go, it will be going one way or the other. So negative acceleration would mean that it is accelerating in the negative direction, which I said that was positive, so it's going to go in that way.
So it depends on your coordinate system that you define as well.
All right, so all sorts of bundled questions in this. All right,
My
let
question
me,
is like similar to his, so.
it is, but there's a small variation to it. So how about if I tackle that one and then get back to that one?
Okay.
I'm gonna change it slightly. What if coordinate system is less convenient? I think that will answer your question when we get there. All right. Awesome. Hold on, board. I am going to someone keep that. Those I'm good with, so all right. Newton's second law. Oh, sorry, Jesse.
Oh, no, you're good. I was looking at the other side.
Okay. What Newton's second law tells us is that the total force is equal to mass times acceleration. In other words, the sum. We're going to add them all together. Now, however we want to label it, we have established two different coordinate systems, which have now been erased, but hopefully we'll remember. So if I wrote down the sum of all the forces there, we have MAG sine theta A, I hat, I A hat, minus FT, I A hat, plus YA, J A hat, minus MAG cosine theta A, that is J A hat, plus FT I B hat, minus M BG sine theta B I B hat, plus YB JB hat, minus MBG cosine theta 3 J B hat equals MA AI A hat plus MB I B A I B hat. All right, that's the formal drawn out. This on the left hand side, I have all the forces. On the right hand side, I have the accelerations. Because I'm doing this, I'm thinking you know this part. Yeah, so I might not be answering your question.
So, okay, I'm gonna.
Let me finish this just in case there's someone else, and then we'll narrow down what I missed. So in essence, what I'm doing here is similar to what I was trying to get across right there, is that, well, these are the I hat parts. So the coefficients of I hat must be the same on left and right. So MG MAG sine theta A minus FT has got to be equal to MAA. And then my JAs will have to be equal to 0 because I don't have anything on the right-hand side for that. And then my IBs have to be equal to the IB part over here, and then the JB would have to be equal to 0 because there's no JB part on the right-hand side. Because ask your question again, maybe it'll clear up how to approach this.
Sure. So my question ran along the lines that we have two coordinate systems that we're working with right now, right?
Correct.
So in your example here, you're giving an example of essentially with what you just put up there, 5x would have to be equal to zx because they're both coefficients of x.
Right.
But my question is that the two x's aren't really the same because they're describing different directions on the two separate coordinate systems that you set up.
The two x's are the same. The fact that the IA and IA here are the same, IB and IB, it's a different thing.
Okay.
That I'm not making the claim that IA and IB are kind of the same thing. I am.
Okay, all right, I see.
Okay.
I'm good.
All right, so I'll just stammer through the next answer, and maybe that'll work. So, right, now let's see if I can address that one. Suppose we set up a coordinate system like this. So IA hat, JA hat, and then for this one, IB hat, JB hat. I think this will get to what you were asking, but if not, then we'll go through another round. When you do the equation and you have this equal to MA, recognize that the acceleration here is in the same direction as IA hat. So therefore, this WA sine theta A, or MAG sine theta A, and that will have the same sign because they're in the same direction. Over here, if we had chosen a different coordinate system that didn't match it, then wow,
Acceleration
we would
it be negative?
Yeah, negative we have to show up. I was hoping for a little bit better rationale than that. But, I mean, there's a fiscal restraint that these two things do have to go together. So if we're saying that acceleration is positive in that direction, then this acceleration would be negative, and you'd end up with, let's see, so this would be, that would be negative, that would be positive, because we said down the ramp was the positive direction. And acceleration would have to be up the ramp.
Okay, that actually answers my question, that makes
Okay.
sense. Because basically it's just like a simple sign flip,
Yeah.
the way you define your coordinate system.
If you wanted to keep the accelerations independent of each other, then we would assign this as, say, a sub A and that a sub B. But at some point, we'd have to reconcile what's the relationship between AA and AB. Because you'd end up with one too many unknowns.
And they'd be opposing each other.
Yes.
Okay.
So if we just, whenever we're dealing with a problem like this, if we just make an assumption, based on where we think the acceleration is going to be and set up our coordinate system such that each of the moving objects would be moving in the positive, or would have acceleration in the positive direction, then we can use this to figure out
Yes.
which way it's actually going to go.
Yes.
Okay.
Enrique?
So you said if we assumed the acceleration was going in the opposite direction, we would have gotten like a positive acceleration at the end?
Yes.
And what values would change, like, in, like, all the equations?
The only thing that would change, if we had, so switched our coordinate systems around from what we did when we actually worked through the problem, not from this, but from when we worked through the problem. What would have changed is that would have been negative, positive, positive, negative, just the signs on this side would have changed. Which would in turn flip these two terms around. And so we'd have gotten a positive answer in the end. Now, I have had some students, I gave a problem like this where I had multiple parts. Part A was, it's frictionless, which way does it go? Part B, then I added friction in, so I did it step by step. So by answering part A, you basically are going through this already. I have asked the question where I did not throw in that first step, and some students just guessed which way friction was acting. Or they had either an intuitive sense or they just got lucky. So it is a tact, not necessarily a high percentage tact, but sometimes it's not easy to tell when I'm grading the student had insight or if the student just got lucky.
Are we good?
Roberto, then awesome.
Yeah. Somehow, it's a little bit strange, but it works. The acceleration in A, that is, I say IA, or I don't know how you pronounce it.
IA.
Yeah, is, okay, going like that, and the other one, B, that is IB, is perpendicular, it's 90 degrees. It's supposed to then not to add to the other one because it's perpendicular, but really, a scalar is the tool that you have to add. No?
Yeah, in this particular case, I realized this as I was writing it down today. I don't know if I intended to do this last time. This is a right angle up here. I'm going through the technique as if this is not. There's some additional shortcuts in this particular case just because this happens to be a right angle. But I was hoping to avoid those.
But where I'm going is that normally those two forces will not contribute at all one to the other one because they are supposedly to be perpendicular, but because they are in a tension cord through the pulley, whatever movement one goes to left or right, the other one goes also.
Yes.
Then and the forces are going to be, like they say, translated to the other side also. Those two must be. Let me see if they are equal. No, you can add it. You can add it, even if they are perpendicular. It's very strange, but it works.
You're talking about adding the.
Yeah, the first equation that is on IA.
Right.
And the third one that is in IB. Those two things go together, no? And that's what you did.
Oh, yes.
Yeah.
It's
Scalarly, they add.
And that's why I chose the coordinate system the way I did, so that they would add and the tensions would cancel out. That was by design. So that's true whether that's a right angle at the top or not. I feel like I missed what you were saying though.
No, it's just that if they were just vectors on an object, those things will not have to do anything one to the other one because they are perpendicular, no?
Ah.
They're and you just decomposing everything. But in this case, because it's a pull in the middle, yeah, you can add it scalarly.
Yep. Yes. What I hear you saying is that ordinarily perpendicular forces do not affect each other,
Mhm.
and officially this tension and that tension are perpendicular to each other because of the geometry of it. But the root changes that. Right. Anything else before? Actually, I want to, before we get into throwing friction into it, I at least want to set up the problem of if you choose this as your coordinate system. I don't wanna solve it because it's a pain. Well, we should get the exact same answer. Like weight down, normal force this way, tension this way. And then that's A. And YB, WB. If we choose that as our coordinate system, I hat, J hat, let's go ahead, what the heck, let's make it the same for both. Let's just make it a real pain. So weight, we don't need to break up anymore. We need to break up normal force and tension here.
So you don't break it up because the weight is in the negative J hat direction?
Exactly. So this one would actually be broken up. I'm going to cut through some of the math. We have WA acting down. This will be YA sine theta A, YA cosine theta A. Just because I did a problem similar recently. The tension is perpendicular to that, and so the horizontal component will have the opposite trig function. So since that's sine for the y, this will be a cosine for the tension. Cosine theta A, and then up would be tension times sine theta A.
So I know that's right, but like, I keep thinking, since that's y a sine theta A, wouldn't that just be the same but negative?
No, because they're perpendicular to each other, because if this angle here is theta, that angle there is the complement, which means that angle there is theta, which means this opposite side is the sine and the adjacent side is cosine.
That makes sense.
So, like, if you don't wanna work it out as a general rule, the sine theta goes with the I hat direction?
I hate to make that generalization.
Okay.
If you are given the angle relative to the horizontal like this, then down the ramp will be W sine theta, and if you're breaking up normal force, that will be Y sine theta. But you have to be given the angle relative to the horizontal,
Okay.
and I'm not thinking of an exception right now. I'm trying to come up with something bizarre. All right, so my equations of motion here, I'd have YA cosine theta A plus FT sine theta A minus WA is equal to mass of A times, well, since acceleration is not actually going to, acceleration is going to be down the ramp or up the ramp. In this coordinate system, that means I have two components for acceleration. So I would call this A sub A I, because that was that's my J equation. Some subscript to indicate what it is. My other equation would be FT cosine theta A minus YA sine theta A is equal to M sub A sub I. I have acceleration broken into components. There actually need to be another equation. The fact that AA sub I squared plus AA sub J squared is equal to A sub A. And then we'd have another set of three equations for the other mass, and then just go to town and solve it. Yeah, it's a mess. Choosing the coordinate system can greatly reduce the amount of math you have to do. I guess, or it could greatly increase. I'm going to end it there, just because it just gives me an idea. So we now know which way this thing is going to go. Let's switch our coordinate system here. Which means our signs change, but that's still gonna be the same. So our forces parallel to the ramp will change signs when we change the coordinate system. We also have to bring friction into it. We know friction is going to act on mass A, not on B. Which way will it act on A?
Positive direction.
And fight. Why positive direction?
Your answer would be positive because the side flips now.
Well, let's not flip it twice. Let's up the ramp is positive now.
Yeah.
So you're saying friction is going to be acting up the ramp?
Yeah.
So you're going down the ramp.
No, the friction, the box try to advance and the friction try to stop it.
So we have this friction here. And so somewhere throw in a negative friction. So I'm guessing that's what you were trying to say.
In essence, sort of, yeah.
Close enough to get credit?
Yeah, I won't take credit for that.
Okay. Now when we do our substitution, I guess they're over here too, so negative, positive. We're throwing in a negative cap over here. What's the formula for friction?
It's the coefficient times the normal.
All right, so friction, kinetic friction is the coefficient times the normal force. Static friction is less than or equal to the static friction times the normal force. Is this static or kinetic?
Kinetic.
Why?
It's not staying still. Or actually, it would have to overcome the static.
It doesn't.
Let's find out.
So, and why as a student I hated these problems? All right. I do keep that in mind. Sometimes I do go, yeah, I want to see them work through the process. But I do keep in mind that I really hated the fact that we're going to basically solve this problem 3 times potentially. When trying to figure out if it's going to move or not, we assume maximum static. Because the static friction is always enough to keep it from moving, and so we have to assume the maximum amount. We know which way this thing's actually going to go. We know friction's got to be acting down the ramp. So this F we will assume is F sub S. So over here, oh, there's one. We make the substitution. This is negative U sub S times Y. Y sub A. And I do recognize I had the beauty of just taking a marker and just changing signs there, but you potentially are rewriting this stuff, so let's do a pause for like people rewrite. Awesome.
Is it necessary to then flip our coordinate system and then go back through, change all the signs?
So again,
No. I mean, if I remember correctly, when we first started the problem, we started off with I had going this way and IB had going that way. And now we've flipped it so that it follows where we're getting positive acceleration, right?
No, you don't necessarily have to flip it around. Just for whatever reason, I like positive acceleration.
Okay.
That's a neat thing.
So as long as I have that established, whenever I'm doing a problem like this, doesn't matter.
Yes. So what I would expect is well, let's talk about, if it moves, given the way I switched the coordinate system around, what do I expect the acceleration to be? Yes. So if you kept the coordinate system we had before, if it moves, you would expect the acceleration to be negative.
Okay, all right.
So now, we have to use this, because friction is now involved. And so, I have negative US MAG cosine theta A minus MAG sine theta A plus the tension is equal to MAA. This equation stays the same. If I add them together, the tensions go away. And I'm left with negative mu S MAG cosine theta A, or theta A, I don't know why I drew that so big, minus MAG sine theta A, plus MBG sine theta B is equal to MAA plus MBA. So very similar to what we had before, except we have this additional, the friction term thrown in.
So what equations did you just combine?
I combined, so this equation became that, when I there's my y sub a. And then I combined this equation and this equation.
Okay.
So acceleration equals MBG sine theta B minus M sub A G sine theta A minus US MAG cosine theta A divided by MA plus MB. Okay, you've already done it? Okay.
Make sure it's not picking up the cord.
Is it alright if I record this?
Nope. So my film's not good enough.
I just don't want to twist my head around for like 2 hours.
No. I assume that was a slam at the number of sideways videos I've done?
Yeah.
Okay. Fair enough. But if yours turns out to come out sideways, what would you tell me?
I could just leave it online before I upload it.
Okay. All right, do we have an answer?
I have a negative
Yeah,
number.
me too.
Yeah,
That's all-
you got negative what?
Negative 2.889 meters per second
That's
squared.
what I got as well.
Kyle, you the same?
I'm still,
I was trying to like break it up into pieces and see if I had.
All right, so we got a negative answer. I'm not real shocked. What does that mean? This right here is the maximum static friction. We did not overcome it. Therefore, if this were a test problem, the question is, what's the acceleration? The answer would be, this is not the acceleration. This is the indication that it's not moving. We did not overcome static. And therefore, acceleration really is 0 meters per second squared. Don't worry, we're about to change something. Because this problem just doesn't feel quite complete unless we've done it 4 times. Good thing we chose the coordinate system the way we did, otherwise that would probably be the length of the entire task right there. All right. Questions before I change it slightly?
What are you gonna change?
Well, one of the questions I ask is, I want to get a positive value here. I want a positive value, so what can I change to make that happen?
The initial velocity?
Oh, well, that's true. Without changing that.
Lower the static.
Oh, I could change the coefficient. If I change the coefficient of static friction, I don't know, I'd have to, use of S is not going to be smaller than use of K. At least I'm not aware of any materials where that happens.
You can change the weights.
Let's narrow that down. I'm going to nitpick that one. I never told you the weight.
The mass.
Ah, yes. I can change the mass. So what do I do to the mass to make it work? Mass of what?
You can raise the mass of B to 15.
Do what?
15 kilograms.
15? Let's do it then. I could have also made the angle steeper. This is the driving force right here. This is the positive value, so I'm either making MB bigger, potentially move this to a different planet. No, that wouldn't do it because all of them have G in it. Or make sine of theta bigger, in other words, make the angle steeper. So let's change M sub B to 15 and see if that is enough.
So we're trying to get an acceleration greater than 0?
Yes,
Because why? Can you say that one more time for me?
because I want to, yeah, I want to deal with the problem where it moves. Because I'm anticipating your want. You want to see a problem where it moves.
I understand it now, sorry.
I got 41.19.
Yeah, what again?
41.19. Oh no, I might have said it wrong.
40, that's the final? Yeah, I will tell you that I feel very sure that can't be right.
Yeah.
It should not be bigger than 9.8.
What did you get?
41.19. I'm pretty sure I put something wrong.
Did you divide by the total mass?
Oh, no, I didn't.
Ah,
No,
okay.
that's not that good.
I guess total mass is now 20.
2.059 meters per second squared.
Yeah, 2.06.
Okay. I'm assuming that they are correct. Unless someone comes up and goes, whoa, no. All right. So, is that the acceleration?
No,
Why not?
because that just indicates that we overcame the static friction.
So now we go through it. Because once we establish that it does move, we're now dealing with a kinetic situation. Now, fortunately, we don't have to go through all the math again. All we have to do is just change this to a K.
Why isn't there another symbol for, like, defining the static friction? Instead of, like, it has A for acceleration.
So, sorry, ask your question again?
Like, why is it like A of S or something like that for the symbol? Differentiated from just the normal acceleration.
Oh, just, would the advantage be just so that you're keeping track which acceleration you're actually finding?
Yeah.
The tradition doesn't do that, but there's nothing wrong if you want to
Okay.
add an extra subscript so that you keep track of where you are. The static acceleration and kinetic acceleration just aren't terms, so you would be creating them.
Okay.
You shouldn't say aren't common terms. All right, so what do we get now?
2.37 meters per second squared.
I didn't tell me.
Oh.
Yes,
What's your-
I got that.
All right, there we go. And at last we put a nail in the coffin. The stake through its heart. Pick whichever you want. Fun times.
That was a lot of work for probably.
Yeah, it is. Only 37 more parts to go. So recalling back the question that I asked, I know it was on a 151 test, I think it was on a 251 test also, where I gave you I gave you all the information except for one angle, and I said, what angle is it in equilibrium? Or, define that one, and then change that angle, so at that point you knew which way it was gonna go. We'll leave that to your own, your own pleasure.
So in a homework or master study, question like this, would the mass already be correct? To give a correct.
Yeah, what I would probably do on something like that is I'd set up the first time, and then I would, throw an interjectory sentence saying, and through some forces, through some magic, mass B suddenly doubled in mass. Depends on the context and the story I'm doing. It's been a while since I've done a story. Maybe I should do one again. Students are not as enamored with the stories as I am.
They throw you off.
Yeah, that's,
Unnecessary words.
was that?
Unnecessary words.
Killing
Yeah.
trees, wasting ink.
Oh, don't forget, I'm old enough. My generation's not gonna have to deal with the environmental problems. Yours is.
Thanks.
National debt too. I'm gonna be dead by the time that becomes a real problem.
What if we make you immortal?
Then I would have to change the way I do things.
You're important, but you wouldn't have to worry about it.
Except I don't wanna live in a barren landscape when everyone else is dead. One thing I learned from a classic Star Trek, immortality consists largely of boredom. All right. Goodbye. old friend.
Do you have some examples? I assume that you have some examples of these that we can work through in the old tests.
Oh, yeah.
Okay.
And if you're doing one where I don't have answers, just ask, and I can either, if I got them with me, I can look it up and see if I can find that test with a
And then you
solution.
gotta do it.
Yeah. I should be doing it anyway. But if you see the ones where there's no solutions, but I have a solution for a problem, that's because the student asked for a solution for a problem. All right. Now the book and mug problem, and then we'll get into something different.
Is this still chapter 5?
I would think this is actually closer to, this is more chapter 6. I think chapter 5 is more concept, the basics.
Okay.
Book. Cup. Or mug, make fun, let's make it a mug. This thing is tied to the handle. Initial velocity, or initial speed, 10 meters per second. This angle right here, make it 30 degrees. Use of S is 0.5, use of K is 0.2. So mass of the mug is, we'll make this, we're using that number, 0.6 kilograms. Mass of the book, we'll make 1.2 kilograms. This was originally a test, this was a question from the previous textbook that we used. So it was how far up the ramp will the book go, and will the book slide back down? You know what, we can go ahead and answer that. Will book slide back down? Take it step by step. If you know shortcuts, just sort of, they'll go along with the process that I'm going through right now. First step. All right. Now, all I really care about are the book and the mug, so let's just do those two.
Is that the friction for the entire problem, or the entire plane?
Sorry, ask it again?
Is that the friction for, or not the friction?
It's the friction between the book and the ramp.
Okay.
Is that, okay. And the book is initially going up the ramp. So, a force. We're checklist F down.
So wait.
Tension.
So we get the tension at each end and weight of the two objects.
So you don't care about the other pair, right?
Right. Just acting on,
the book, perpendicular.
why is there no normal force on the mug? Okay.
No. Any more friction right now?
Is there friction acting on this thing?
Yes.
How do you know?
You've given us new values for it.
Yeah. Which way is friction acting on the book?
Opposite potential.
Okay.
I mean, initially, I'm like, W.
Alright, so I'm saying, which way are you pointing at? Not quite sure.
That way.
That way. So there seems to be an overwhelming support for the friction acting down the ramp. Friction opposes the motion, the relative motion. The book is it starts out the problem going up the ramp. So friction has to be opposing that. And it is kinetic because the book's already moving.
Could you explain again why there's no normal force on the,
It requires contact. The normal force is something which basically pushes another object away. So the ramp is keeping the book from smashing into it, so it's pushing away on it. The only thing the mug is touching is the rope or string, whatever this is, and we're lumping that into tension.
Now, why is it up of K?
Because the book is already sliding. K is kinetic when the two objects slide against each other.
Got it.
Static is they are not sliding against each other.
Why is there use of F then, or use of S?
Why not?
Because it starts off in the problem moving, so it doesn't need to overcome.
Yeah, so it's information you don't need.
Okay,
We actually will need it for the second part, but you don't need it for the first part.
okay.
I would much rather give you information you don't need than suddenly realize I forgot to give you something important. All right, so the direction of acceleration of the book. One vote for up. Everyone got Courtney's back on this? Austin, that was that a no?
Yeah.
They said that the accelerated, no?
When
That's
it's
negative.
accelerating due to the gravitational force?
Well, I mean, all right, is the book gonna slow down or speed up?
Going down.
So if it's moving up the ramp and slowing down, what's the direction of acceleration?
Down, negative.
The other indication that the acceleration can't be up the ramp is there are no forces acting up the ramp. All the forces are either perpendicular to the ramp or have some component down the ramp. So now the question is the coordinate system. We can make the coordinate system so that part of it's down the ramp, in which case I will expect a positive acceleration. Or we can make it that way, in which case I'm expecting a negative acceleration. It doesn't matter which one you pick, it depends on what you're comfortable with. So, coordinate system, you want down the ramp positive or up the ramp positive?
Down the ramp.
Okay. I'll call it I hat, J hat. And so by convenience, since we're making down the ramp positive for the book, we should make down positive for the mug. Since the mug is just a one-dimensional problem, I can get away with it by just saying down's positive. If you want to have a letter, you can call it, I2 hat or IM hat. So do we need to break anything up? Decomposition time. Yeah. We're breaking this up. That is the one thing. This is in the J hat direction. These are in the I hat direction. That's in the positive direction. That's in the negative direction. This is the only thing that can't be expressed as a single unit vector. Taking this theta here. So we have tension acting down, we have F sub K acting down, and then we have WB sine theta acting down the ramp. Into the ramp, we have WB cosine theta. So I take out the weight from the original one and replace it with the two components.
So, how did you know that was sine and cosine?
Having done these enough, but, all right, so the breakdown is, I have the force I'm breaking up is the one that's going straight down. This angle here is theta. Whatever I'm breaking up is the hypotenuse of a right triangle. And so I'm gonna break this up into, I got part of it going down the ramp, part of it going into the ramp. That's a right angle. This is weight. So I have a right triangle here, so if that's theta, this is the complement, so I'll call theta prime. This is a right angle here, so this must be theta. And so now the opposite, that side right there is opposite theta, so that's why it's sine. Is that sufficient? Alternatively, let's say that you're in test, you're in panic mode.
Parallel to the ramp, would that always be sine?
That if, again, this goes back to something Max was asking earlier, if you're given the angle relative to the horizontal, down the ramp's gonna be sine. Into the ramp will be cosine. If you're in panic mode, almost all the angles I ever draw look like 45-degree angles. That's why I have to label them. So what I could do is try to draw something more realistic. And so now when I break weight up, I have weight acting down. Some of it's going this way, some of it's going that way. I draw my right triangle. Again, trying to draw this somewhat accurately. I have two sides here. This one is shorter than that one. So for 30 degrees, sine is smaller than cosine, or do it on your calculator to figure out which one's the smaller one. That's the smaller one, that's the larger one. Now, if you're in panic mode, are you going to think to do that? I don't know. But it's a different way of looking at it. Other questions up to here before we do our equations? All right, who has not done an equation of motion yet? Just chime on in.
So we're not gonna have the I guess it'd be for the mug, we're not gonna have an I for the mug. That's for mug.
Right, how many equations will we have for the mug?
One.
Yeah, so we'll only have 3 equations. If you wanted to, you could do a horizontal equation for the mug, but it would be 0 equals 0, which is a true statement. So the math people tell us. But can they prove it? All right, equations of motion.
Is it, WB sine theta plus FT equals MA?
Two issues.
WB cosine theta.
No, that doesn't come in yet.
Missing F of K.
Yeah, there are 3 forces going down the ramp.
So you have one of them.
So plus F of K. And the other issue, I've seen a lot of students make this mistake, and sometimes they correct it and sometimes they don't.
They don't specify the mass, like you have to put B, mass of B.
Yeah. We have two masses in the problem, we need to differentiate. There are no forces in the negative direction, because of the way we defined our system. All right, one down. Next.
What is it, negative WB cosine theta plus one? Minus one? Or plus one?
Which one?
Minus.
Plus,
Okay, you feeling good with that?
I think so.
It comes down to the positive direction is that
Positive,
way.
right, so it's plus one.
Yeah, it is.
Is equal to zero?
Like you mean it.
Zero.
Yeah. Unless it's a really strange problem, you want one of those equations to be equal to zero.
So is that always, is it like, so if there's only two forces opposing each other, it's gonna be equal to zero?
No, it's zero because we know which, there's no way that this book is gonna be accelerated that way or
Yeah.
around.
Okay,
That's why it's equal to zero.
common sense.
That's the hope. Again, panic mode on the test, common sense isn't necessarily there. All right, one more equation to go.
WA minus F of T. F of T
Yeah, thought that's what you said.
equal to MA. MMA.
We're only the toughest survive. All right, so what's next? Kyle?
So I'm struggling to see what equation to need. Like, I know where the equations come from, but like,
So you're good from this step to this step? Oh, okay. Sorry, do you want to, I cut you off, sorry.
so your base equation is mass,
This is, so this side is the force, and this is mass times acceleration. That's what we're doing each time.
okay.
I think it helps putting the coordinate system right beside your box.
Okay,
That way you
here?
almost like visualize it where it's going.
So that is my I hat equation, this is my J hat equation, and this is my other equation.
Okay, that helped, yeah, that solved it right there.
Okay. Any other questions before someone dazzles me with what we do next? All right, dazzle me.
Do you wanna combine the two equations?
Ooh, not yet.
Weight is equal to mass times gravity.
Gravity.
Acceleration.
Thank you.
Uh,
I'm figuring you'd write it down correctly, it's just,
Would you write the first one and the third one?
Sorry.
like childhood scars. All right, so I have M, see if I can get a marker that does us all proud. MBG sine theta plus FT plus equals MBA negative MBG cosine theta plus Y equals 0 and MG minus FT is equal to MA. Obviously, I left a gap there. What's the other substitution we would do?
That equals use of K times normal force.
So, use of K times normal force. The normal force that you would use be the one at where that friction is applied. Since that friction is between the book and the ram, it's the normal force between the book and the ram. Now in this case, we have only one normal force, so there's not much choice. But I know master set 6, again, I'm thinking it's problem 3, one of the early ones. There are 2 different points of interaction, 2 different normal forces involved. All right, so now, we've gotten this far, done the substitution. I think Marisol, you were suggesting something. You're just ahead of your time.
To run the equations,
How do you want to combine them?
I would add the first and the third one. And cancel out the friction. I'm sorry, tension.
No. I knew what you meant. UK, and then Y, we can just go ahead. I know Y is going to be equal to, if you bring that over, so this is MDG cosine theta plus MAG is equal to MDA plus MM.
Isn't MAG, we don't have an MAG. Yeah.
Oh, wait.
It's MM. I
Yeah.
think you meant M.
Yeah, that, oh,
No,
yeah,
it's
yeah.
M.
Yeah, I looked over here and I saw a letter A. So. That's why I need good handwriting. Only my elementary school teacher had said so. And so acceleration equals MVG sine theta plus UK MVG cosine theta plus MMG divided by MB plus MM. Now we don't have to test to see if it's actually moving. We don't have to figure out the direction of acceleration. It's built into the problem. We already know it through thought and experience. And we are expecting a positive answer. A negative answer would be very strange because we aren't subtracting anything. So probably an indication of, I suspect if you get a negative answer, it's because your calculator's in radians instead of degrees. So what else going on? I have a social question for you. So if someone calls you, someone you know calls you but does not leave a message, do you call the person back?
Yes.
Yeah.
So who's with the nose on this one? Okay,
Actually, yeah, I'm on the note as well.
all right.
Just don't like when people call me, so I just ignore it.
Or I'll text that person, why did you call me?
If they're important enough.
Oh,
then
yeah, you
text
did
them.
that.
If they're important enough,
Texting me,
then
like, what's up?
I'm texting back. If not, if they're not benefiting you at the moment.
I don't like calling.
Okay. If they left a message, I assume that they changed their mind, but.
I got 4.73 meters per second squared.
did you get?
I got 7.66
That's what I got.
meters per second squared.
It's all sorts of fights you're picking today, Marisol, what's up with that?
I'm sorry?
Said all sorts of fights, I mean.
I know.
So it's narrowed down to one of these two answers here.
I got the 7.66.
All right. So Max, I'm gonna go with the majority on this one. I'm not saying you're wrong, Max, I'm just saying, let's just go with this for now. All right, so we have 7.66 meters per second squared. It is positive as expected. And so now actually answer the question. How far up the ramp will the book go? This is now a chapter 2 problem. We have displacement, initial velocity, final velocity, acceleration, and time.
Final velocity is 0, equal to VI plus AT.
What is VI?
10 meters per second.
And acceleration we just found. There is one mistake we have up on the board here. One of those is wrong.
Which coordinate are we taking?
Which one? We switching coordinate system now, or Max?
Either the 10 meter per second or the 7.66 would need to be negative.
So one of them, they're in opposite directions, so one of them has to be negative. It doesn't matter which one. If we make this one negative, we switch our coordinate system to up being positive. If we make that one negative, we're sticking with the same coordinate system. Pick one. You would notice if you did ignore that and you solve for time, you'd end up with a negative time, I believe. Yeah, you'd end up with a negative time, and that would have been an indication of, oh, wait a second, something's off. It doesn't really matter which one you pick. So using the VF equals VI plus AT, we have 0 is equal to negative 10 plus 7.66t, and so t becomes 10 over 7.66. We don't necessarily have to solve for time. There are other ways of solving for it than answering the question first, but we're here.
1.305 seconds. Or do you want more numbers?
No, that's fine. I was trying to tell if, I thought I heard another number in there, which I left off, so that's what I was looking at you to see if I left the number off.
So why did the initial velocity and acceleration have to have opposite signs?
Because the acceleration, when we solve for acceleration here, we assume that down the ramp was positive. But the book is going up the ramp. So that's why they're opposite signs. Now what in order to find the displacement? Which one?
Change x VIT plus 1/2 AT squared.
So negative 10 times 1.305 plus 1/2 times 7.6, 1.305 squared. I do expect the answer to be negative. Negative 6.
meters.
My page is because they're rounding, but I got 6.4, negative 6.477. It might just be because of the rounding.
I assume you did 1.305 and you did the full number, or vice versa?
I did 1.05.
Okay.
And I also used a different formula, but it's just.
Oh, you use a different formula?
You
I
did.
used the displacement equals initial velocity minus final velocity equals t times time.
Oh. Wait. Which one did you do again?
Displacement is equal to initial velocity or final velocity over q times plus final velocity over 2 times time.
Okay. VI plus VF?
Yes, over 2.
Over 2 times time.
Never mind, she's right. I did something else.
So
Now, oh, sorry.
Is it negative because it was in the, going in like the negative direction of the
Yes, it
forces?
is. Yeah.
So would we write the answer as a negative? Or
You
would we
would,
write it-
the way that it's worded right there, you'd write the answer as a positive number.
Okay.
How far implies distance. So will the book slide back down? Oh, questions on this before we tackle the second question? All right, so once the book gets up to the top, and then it's going to either stop or come back down the ramp, the question is, will it slide back down? What changes in, let's start from over here. What changes in our force diagram?
Friction to the other side.
Yes. So friction flips over to the other side. And we're trying to determine if it's going to move or not, so we use static friction. We'll use our maximum static, actually. Max. And so, for the power of the eraser, and, oh, here it is. So it's not a huge change, but it is a fundamental change that happens through all the equations. So if it stays, what should I expect the answer to be?
Like,
Right.
or exactly 0.5.
No. That 0.5 is a coefficient. 0.5 is not friction itself. A common mistake. Let's see where you want it. I guess negative or 0. The answer is.
I have a positive number.
You have what?
I have a positive number.
Okay. What you got?
Actually, no, sorry. I'm confused something wrong.
Now your calculator don't know how to change from radians to degrees.
That's a positive number, 3.703.
3.073.
3.703.
Dyslexia of the ears. So follow-up question were, what is the acceleration? What would change? Or are we done?
Well, you know it moves and you have to change it to use of K.
Yeah. So that changes to mu sub k. We get the actual answer. And as exciting as doing that is, I'll leave that to your own. You know, when you go home, next time you're with colleagues or other classmates or loved ones, hey, let me show you how to do this.
Probably bore them to death.
Yeah, they probably would blew me out.
Yeah, they wouldn't pay attention.
They probably would not.
I try to teach, like, just because it helps you memorize the
Right.
concepts, no one pays attention.
I think you need better relatives. There was a sitcom years ago that played on the idea of you can't pick your relatives, and there was somebody who actually put out an ad for his relatives. So he picked them. It was a short-lived sitcom, not particularly funny, but an interesting idea. Questions? All right, let's take a 10-minute break, stretch legs, get the juices flowing again. We'll come back and I'll throw things. Sling is probably a better word. I'll sling things.
I have a question about
Yep.
so, for the
Luddites, anti-technology. They were the ones who, no, I'm confusing two different ones. Yeah, against modernization. All right, so tension is the centripetal force. And for the sake of the camera, centripetal force is not a new force, it's just a combination of the stuff we've already done. Okay. Now we've gone through and derived and back to the question I did ask before. We already did the centrifugal thing?
Yes.
Okay. So we still plug into F equals ma. That doesn't change. The only thing that's changed is the acceleration is a little bit different. In this case, we have tension is equal to mass times acceleration, except this time it is centripetal acceleration, as Mario indicated earlier. I think several people did. Centripetal acceleration. And we have a formula for that. And what is the formula for centripetal acceleration?
V squared over R.
Or
Omega squared R.
that's the other one. What is omega?
It's the change in theta over radius, isn't it?
Not over radius.
Oh.
It's the speed, yeah, radial speed,
Angular speed.
negation.
Radial speed would imply the speed going towards or from the center. Angular speed based on the angle. All right, so this is angular speed. This is linear speed. What's the relationship between linear speed and angular speed?
What was your question again?
What is the relationship between linear speed and angular speed?
Is it WR?
The spirit of what you're saying is right. Let's see if we can get the language down.
Oh, sorry, omega R.
C equals omega r. It's like the distance or arc length is equal to the angle times r. This assumes that theta is in radians, omega is in radians per second. I guess you could do some funky unit there, but that's tradition. So tension is equal to m v squared over r, or m omega squared r. Now you don't have to write both of them every single time. Which one is more convenient really depends upon the problem. There are some problems where this makes the math a whole lot simpler, and some problems where this makes the math a whole lot simpler. And sometimes you don't know until you try them both. So let's actually work on a problem here. I have some car traveling around a circle, a radius r, at some speed v. If this track is flat and frictionless, that car would just go that way. Recognize when you go around a curve, you, I hope, have never gone straight on a curve. But what's keeping your car, when you, let's assume flat road, you go around a corner as you're taking a turn onto a second, on another road, what's the centripetal force? There's gotta be something keeping you from traveling in a straight line.
Right.
Like you mean it.
Friction.
Yes. It's friction that's acting on the car. Which way does friction act on the car to keep you from traveling in a straight line?
Towards the center. Towards the center.
Yeah, the centripetal force is always towards the center, the radius towards the center of the curve. Now, in reality, you rarely have a perfectly round track. You have, well, assuming everyone in here is driven. The radius of curvature changes as you drive.
Sorry.
But we'll deal with a nice ideal at the moment. So let's assume, let's start out with a bank track. Let's say no friction, so it's frictionless. And banked track. In other words, the track is at some angle theta. The car is going away from us. Taillights, which look a lot like the headlights that were coming towards us. What I want to know is that speed so that car does not slide. I should say car does not slide up or down track. The process is identical to what we have done. First step is
What's that x besides the velocity?
was that using the three-dimensional notation that the x represents into a surface and a dot is coming out.
That arrow thing?
Yes, that's the thing. So, forces acting on the car.
One.
Friction. Against.
Uh,
Oh, wait, no friction.
frictionless for right now.
Normal.
That force diagram looks the same as Boxhole frictionless ramp. And here's where the difference is. So we got the force diagram done. Acceleration. What is the direction of acceleration?
The direction of the normal force.
So it's going to, so if
Or,
it's that way, you're dealing with it speeding up. So we're assuming it's going to travel at a constant speed. So there's no acceleration in that direction. Because there's only so complicated I want to make it yet. If the acceleration's that way, direction of normal force, that means that the car is going to be coming off the ramp. Let's assume that the car does not come off the ramp.
So are you saying it would go into the ramp?
If acceleration is into the ramp, that means the car is slowly digging into the ramp.
it's like this way, the car is going. Not this way. This is normal force.
So you have it pointing
Into the page.
into the page.
Yeah.
If the acceleration is in the direction of the velocity, the car will speed up. We assume constant speed.
Is it towards the center of the circle?
Yes. Which way is the center of the circle? Got a couple people pointing in the right direction and some people
It's like,
trying to figure out.
I don't know how to word it.
Given the way I've drawn this, this is at this point. That's always going to be towards the center of the circle, and I just happen to take the snapshot at this point right here. Acceleration is going to be that way. The most common mistake I see from students is they have acceleration down the ramp. It is towards the center of the circle. The car is traveling around in some horizontal circle right here. It is not traveling in some circus motorcycle inside a cage thing. That's the only time I've ever seen people driving like that. So when I set up my coordinate system, the acceleration being parallel to, I guess ultimately the Earth, is the big difference between this and Foxhole Ring. So what am I breaking up? Yes. And so this will be y sine theta, y cosine theta. Actually, last time I think I just jumped through that. Let's do the math. So some angle theta here. My normal force is this way. I go ahead and extend that. That's a right angle. This is supposed to be. I'm breaking this up into perpendicular components. If this is theta here, this angle right here would have to be the complement. I have two parallel lines transversed by a, blanking on the language that I learned 40 years ago. Two parallel lines cut off by another line. We have corresponding angles. That angle there would be theta prime. Or alternate interior angles, that's theta. But ultimately, that angle up there is theta. So the opposite side, the one that is horizontal, is the sine. The other one's cosine. How many equations of motion will we have? Okay. We don't care about the direction of traveling, we care about acceleration. All right, so what are my equations? I'll have an I equation and a J equation. If I did have him speeding up, if I threw in friction and allowed him to speed up or slow down, then we'd have it'd be a three-dimensional problem. That would be fun. So what are my equations?
Y sine theta is just equal to mass times acceleration.
Yep. And just putting a little C there to acknowledge that it's centripetal acceleration. And the other one?
Y equals minus W, 0.
Substitution. For what do I have a formula? All right. And
G.
we have a formula for G.
I don't know how to say it. The vocab.
We have a formula for weight. There's no G in this equation. That's part of the issue. For the stuff we have in this equation, these equations here, what else do we have a formula for?
Acceleration, centripetal acceleration.
Yeah, we have an equation for those two things. So y sine theta is equal to mv squared over r. Why v, not omega? Because that's what I'm asking for, v. And the second equation, y cosine theta is equal to mg. And so now, it's a matter of solving. We're solving for v. There are a couple ways of doing this. The simplest way is just to divide the equations. If I divide the left sides and then divide the right sides. If I divide the left sides, the y cancels out, and I'm left with tangent of theta. The right-hand side, the masses will cancel out, and I'm left with v squared over gr. Or for those feeling saucy, RG. And so D is the square root of G, R, and theta. So now let's stick it on some planet. Let's just pick a random planet with acceleration of gravity about 9.8 meters per second squared. R, let's go with my classic go-to, 100 meters. And then tangent of, I didn't give an angle. Let's make it 30 degrees. Alright, so that's 23.74.
786, so close. 6. Peter,
I got 784.
781?
I got 784.
784?
I got 7866.
Yeah, so that should be
So they're probably right.
rounding off.
So many places, you know, on a tester quiz, I would not notice that difference. On the lab, I might. All right. Our first centripetal motion problem. Should be feeling the surge of endorphins. Can't wait to tell the folks or the kids or the siblings. But just relax, it's not over yet. You'll have more to tell them by the time you get home. Questions before we throw friction into it? So let's throw friction. Oh, I'm stuck in a rut there. Oh, let's mix it up. There we go. Mu sub S is 0.4, mu sub K is 0.279. Ooh. Yeah, I know how to live on the edge. And so now the question is, what is the maximum speed this car can go before it starts sliding up the ramp? I know it can do 23.786 meters per second with no problem, or sorry, 6. But with friction, I should be able to go faster. So what changes?
Horsepower ground.
All right, so where does friction go?
Against the ramp or against the car.
Going that way?
Yeah.
All right. So I have friction, static or kinetic?
Well, it's already moving. So kinetic.
Question is, are the tires sliding or are they rolling? So we'll assume an ideal roll, so we're not worried about rolling friction. We assume an ideal roll so that it's static, that you're not leaving skid marks as you drive. Static friction. Now, if he exceeds whatever we're about to come up with, then there's now kinetic involved. So we have to break friction up also. So I know part of the friction is to the left and part of the friction is down. The part that's to the left, well, the part to the left for normal force was sine, so this has to be cosine, so this is Fs cosine theta. And the part that's down is Fs sine theta. So now what are my equations of motion?
On the first one, you had Fs cosine theta. Second one, you would subtract Fs sine theta equal to 0.
A more interesting problem, in my opinion, but not as easy mathematically. Substitution phase, we have this, we now have three equations. Weight, we have a formula for, centripetal acceleration, we have a formula, and F sub S. Now, F sub S, the real formula has an inequality in it, but we were looking at an extreme. What is that maximum speed before we slide? So we're assuming we're at that maximum static. So this becomes y sine theta plus mu s y cosine theta equals mv squared over r. Y cosine theta minus mg minus mu k y sine theta equals 0.
Wait, is it Muse S or Muse S?
Yes, that should be mu s, thank you. That would have been a big mistake. We know the angle. We know mu sub s. We know, we don't know m, but it doesn't really matter here. We know r. We're trying to find v. So now mathematically, what do we do?
Don't know M.
We don't know him. You have two choices on the mass. You're faced with, you get this on a test, I didn't give you the mass, which means either I made a mistake and I should have given it to you, or you don't need it. If you don't need it, then make up a number if you want. That's one way of dealing with it. Don't make it 0.
100.
Pardon?
100 would work.
Sure. Is there a reason you want to do 100? Just felt right?
I think I saw a problem be done like that before.
Okay. Depends on at what point you want to plug numbers in. So officially m's an unknown. Personally, I would have gone with 1, but 100 works. So now what? Now I have two equations, two unknowns. One of the are unknown, we don't know normal force, and we don't know speed.
We can set it equal to one unknown.
Which one?
I don't wanna pick one because I might pick the wrong one.
And what's the worst that happens?
They'll blame me if we do along.
Ah.
I've been there.
Yeah, exactly.
How about this then? If you pick the, so you're proposing that we solve for one of the two unknowns, and then what, plug into the other equation?
Yeah.
Well, since there's no v in this equation, solving for y might be the simplest. Sure. There are other approaches, but that works. So we get this over to the other side. So I have y cosine theta minus us y sine theta equals mg. So y would be mg, that's supposed to be an equal sign, divided by cosine theta minus us sine theta. Now what? Stare at the problem.
Are you still considering that mass is 100?
Sure.
But I guess you can just plug and chug.
You can plug in y to the first equation.
Yeah, you can, on the top one, just take out y, that is all that,
Yeah.
and then you gotta be isolated.
Alright, so if you want to plug in numbers at this point, go for it. You can actually come up with a value for y. If you want to hold off, and some people, it's generally recommended to wait, but on a test or quiz, I don't care. If we factor a y out of that, we'd end up with mg cosine theta minus us sine theta times sine theta plus
US.
us cosine theta equals mv squared over r. If you do it this way, the masses can cancel out at this point, so you don't have to have the mass. And then so v is equal to the square root of r times rmg cosine theta minus us sine theta divided by, wait, no, that's not right. That should be sine theta. us cosine theta over cosine theta minus us sine theta. I feel like
It's
something
a
went
plus.
wrong.
Sine theta plus, I think.
So it's a plus on top. I still feel like something went off.
The math.
Oh, okay. I was wondering why us was associated with sine theta, but from that, okay. This is what happens when I take shortcuts. All right, so we got to here, the masses canceled out, multiply times r, and I should have sine theta plus mu s cosine theta over cosine theta minus mu s sine theta. Okay. I'm feeling more confident with this, but I'm not opposed to having made another careless error somewhere. Mu s is 0.4, so that's about a little over 1. So it's going to be 1.7, so about 1.2. So somewhere around 35 meters a second. Yeah, or readjust. 34.2178. Is this the day? Got it. I'm hoping one of these days I'll get it out of 6 significant figures.
Is that 9.8 or 900?
It's R times G, and R is 100.
Okay.
That's where the 980 comes from.
So if you find like the actual normal force by plugging in a mass, do we need to list that in the final answer? Like, will that affect?
Oh, so if you find Y first and then plug in?
Yeah.
The only issue that it should cause would be rounding, which is not really an issue for a test or quiz.
Okay.
So do you come up with the final answer or just?
No. It's-
Okay.
Then just before that's the velocity, it keeps on track and just getting and after it starts sliding.
It'll start sliding towards the top of the ramp. Did I intimidate people by throwing out a guess?
Got 30.38.
30.38? Anyone else?
I've got 35.29, but I have to check again.
I got 27.89.
27.79?
89.
789?
89.
Just 89.
Yeah.
I got the 27.89 as well.
I had a 30.5. But it's also how you input it too.
I got 35.29.
So I'm gonna guess it's gonna be one of these answers, and, you know, put your money on whether I'm right. The big thing, it's bigger than the frictionless situation. It better have been bigger than the 23 point, whatever we had before. 23.784, whatever it was. The 30-degree angle, cosine is square root of 3/2, and sine is 1/2. That, well, good with that. So this is, use of S is 0.4 times it. Then down here, square root of 3/2, and then this is 0.5 times, oh, wait a second. No, 0.5 times 0.4 is 0.2. All right, it's one of these answers, meters per second.
I wish we could do that on the test.
Pardon?
I wish we could do that on the test.
But with that, lots of answers?
Yeah, and then it's one of these meters per second.
And chemistry teacher in high school that if you, on the multiple choice questions, if you had the right one and then you erase it, put another one down, if he could still see what you had written down the first time, he'd still give you credit. Never seemed quite fair, but I never objected at the time. That's it.
I got 35.29. The first one I got was plugging in with your numbers, but then I
Yeah.
manually plugged everything into the formula, and I got 35.29.
What'd you get the first time?
The 27.89.
Plugging in these numbers, you got 27.89.
Yeah, plugging it in exactly like that. I got 27.89.
Why?
Could it
Am I
be-
sine and cosine right for 30 degrees? Sine of 30 degrees is 1/2.
Yeah.
Yeah.
Cosine is square root of 3/2.
Yep.
I think it's the square root throwing things off.
Right, well, we seem to be slowly heading towards a plurality here, at least. You'll come up with some answers as you're redoing your notes. And there's other variations of this problem. Another variation of the problem is pretty much the same setup, except for what is the minimum coefficient of friction so that the car does not slide off at 40 meters per second. And so it's just a different unknown, a different math problem when you get to here, but it's similar.
What you did wrong is you did a plus at the bottom, not a minus.
Ah. Thank you. And apparently my guess was as close as it was because I just intuitively knew that I did it down wrong. Yeah, that's a relief. No mistake was. We're done with chapter 6. At this point, it's a different problem, but it's the same process all the way through. So next Monday, we're not finished yet. We're just wrapping up that before we go on to chapter 7. The master set for chapter 5, let's do next Monday. Tuesday. One of those days next week. I'd like a master set for chapter 6 done before fall break, which I think is the following Tuesday, Monday and Tuesday.
Yeah, the 12th and 13th.
So we should actually have some quizzes in here too. Yeah. And then semester breaks are really good stuff. How about this? Let's put the quiz on chapter 5 on that Thursday. Is that too much? The other alternative is putting the quiz after fall break, and that doesn't always work well either. Because for a lot of students, fall break means, oh, you get to work full time. Right, any objections or any suggestions for a change to the schedule as it's written right now? Okay. Right to that. Now, things are supposed to travel in a straight line. They want to. That's the whole essence of inertia. Things want to travel in a straight line. They want to keep doing whatever they're doing. So since the Earth does not travel in a straight line, there must be some force causing it to change. What force causes the Earth not to travel in a straight line?
Centripetal acceleration.
What force?
Gravitation.
What'd you say?
Gravitation.
Oh, okay. I thought you said tension. That was throwing me. Yeah, there's a gravitational force pulling it in. If we did the full force diagram, forces come in pairs. Where's the other part of that pair?
One side.
So the Earth causes a tiny little wobble on the sun. not significantly, because we're not that massive. But it's basically how we found a lot of the planets, the fact that we see something not traveling as we expect it to, and we go, oh, there must be something causing that. They go through the math to figure out where that would be, and then they look and they find it. Make it sound like it's an afternoon, but, you know, over the course of years. So if I look at this system here, well, it's F equals ma. Newton's second law still holds, except this time we have this gravitational force is equal to mass times the centripetal acceleration of the Earth. So this comes in, what exactly is the force due to gravity? Up till now, we have very nicely just had a formula. We called it weight, and we said it was mg. Well, technically, mg would still work, except I have no idea what the acceleration due to the sun's gravity is, where the Earth is right now. So there must be some more generalized formula for this. And this is what Newton figured out. He figured the masses were involved. Since the magnitude of the forces has to be the same, whatever the two masses are, if we flip them around, the magnitude of the force should still be the same, which means the commutative property should hold, whatever we do with the masses, which comes down to it's either addition or multiplication, since there's no commutative property of division or subtraction. So we have these two masses involved, it is multiplication. The other thing he figured out was how far away matters. Would you expect the farther you are away from the sun, the greater the gravitational pull or the less the gravitational pull? So as r gets bigger, the force gets smaller, so put that on the denominator. And he figured, and I don't know if he calculated to the lucky guess, or actually there is some thought process for squared here. It is r squared. If you imagine that the sun is giving off something, which theoretically we'll call gravitons, that's giving off something which hits the Earth, whatever it gives off basically is expanding out on a sphere. And so the farther out you get, the fewer these things that will hit you. But since the surface area of a sphere is related to the radius squared, it makes some sense that there'd be r squared on the bottom. And the one other factor, that's more what unit system you're dealing with. And so capital G, not lowercase g, capital G, this is the generic formula for the magnitude of the force due to gravity. Let's define some stuff. M1 and M2 are the two masses. The two masses. R is the center to center, technically center of mass to center of mass distance. It is not surface to surface. If that were the case, if you ever went outside and touched the dirt, you'd be stuck forever. Fortunately, it's from the center of you to the center of the Earth. And G is unit system dependent. It is known as the gravitational constant. It is the third thing that students will just call gravity. But it's not gravity, it's an aspect of gravity. It's gravitational constant. If you're dealing with the SI system, it is roughly equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. I will sometimes make a reference to it as the universal gravitational constant, and so I'm going to put universal in parentheses here. I think at this point, textbooks will not call it that anymore because there is a question of, is it universal? We know the value here, but do we really know what the value is elsewhere? The universe does not behave the way we expect it to, and one of the explanations was, well, maybe this value is not universal. Also, just food for thought, even if it is universal, let's say that right now this is the value for G everywhere in the universe, that does not mean that is the value for G a million years ago. It might be universal in space, but not necessarily time. And that's another possibility for when trying to explain the way the universe is acting, because we're basically seeing the past. And so maybe the concept was different. More formally, the gravitational force on 1 from 2, so this is the force on 1 from 2. Big G, mass 1, mass 2, over the distance between them squared, times R2 hat. Yep. Negative. Which means that if I have two masses here, I got a mass 1 and I have a mass 2. Gravitational force is attractive. They're being pulled towards each other. The force on mass 1 is in the negative R2 hat direction. R2 hat is the radial unit vector, where R2 is the center, or mass 2 is the center. So R2 would be a unit vector away from it. The negative sign means it's towards. So mass 1 is, the force on mass 1 is towards R2. Let's do a quick calculation, then I'll hand back tests. So the magnitude of the force of gravity between me and the bowling ball. 6.67 times 10 to the negative 11th. My mass is about 100 kilograms. And the mass of the bowling ball uh, 3 kilograms. The distance between us, .3 meters squared. That's a Newton meter squared. Could have made nicer numbers. Of course I didn't. So let's see.
Rounding up is 1.2 to negative 8.
That's in the negative?
Negative 8.
Negative 8. Units? Yes. I hope so. All of our things are in SI units, kilograms and meters, and that's the conversion for SI units, so it better be newtons. So we're talking the force between me and the Earth is about 1,000 newtons. The force between me and the bowling ball is 0.00000007. Which is why we've ignored all of those gravitational forces when we've done force diagrams. It requires highly specialized equipment. To give you some sense of the people who actually care about that kind of stuff, there was a group looking at gravitational forces, and they were getting different results depending upon the time of year, which they thought very strange. They were down in the basement, which becomes key in a moment. What it turned out was that in the spring, they got different results because it rained more, and the rain would soak into the hill on the other side of the wall, and that was throwing off their experiments. The amount of water that was that soaked into the ground. Those are the people who look at that kind of stuff. I dealt with high energy physics. We didn't deal with those small forces. And, oh, test. All right, test corrections. Rules for test corrections. On separate paper. I don't want to have to go through your test and try to figure out, oh, was that the original work or is that the new work? I don't want to do that. Paper or papers, however many, think that literally resign yourself to just one sheet of paper. Here's the big one. You're trying to convince me that you understand. If you just put down an answer, that gets you nothing.
So does that mean don't skip any steps?
Right.
Just write every step.
Yes. And I don't have a problem if you're working with someone else, but if I see two with identical answers, I'm not gonna play a game of who's the one who did this and who copied. So make sure it's your original idea and thought. Or you're working with someone else, but make sure you're writing it down the way you need to understand it. 251 is usually not an issue. 110 students, horrible at this part. The number I've gotten in with just answers. If you want to know the answers, just ask. I'll tell you the answers. Matter of fact, I'll post them at some point.
What are you exactly trying to convince that you understand?
This is for test corrections. So I'm about to hand back the test. And so you'll be able to get points back. So the points you would get back, if you got an F on the test, so 0.0, you can bring it up to a C, 2.0. If you got an A on the test, a 4.0, you can bring it up to an A plus, a 4.3. And then it's scaled from there. So if you had a C on the test, which is a 2.0, that could be brought up, well, that's halfway between there, so it could be brought up to a 3.15. Now, usually, students in this area have so much work that they have to do, they usually don't get full credit. People in this area generally going, let's just get the low-hanging fruit. It's not worth my effort to, I got an A. So it's rare that anyone ever gets the full credit, but it is possible. That's the big one right there. I would like it in, we'll just say, generally it's 2 weeks, but let's go for 3 weeks, so 20th. Test correction. Now, if it's not ready in 3 weeks, just let me know. I don't want it hanging over your head in December. I wanted you to be done with it, get it off your plate.